All right, so looking at our due now, it asks us for the cost of, or it tells us the cost of a New York Yankees baseball cap is $24. The local sporting goods stores tells it for $30. Asks us to find the markup rate. So originally the price is $24. So if we're looking at percent times whole, our original price is $24. So that's definitely the whole. And here we have a couple of options. It asks us to find the markup rate. We can find the markup rate in a couple ways. We can either find it by plugging in just the difference or the change. That's going to tell us the percent increase. Or we can find it by plugging in the original value. So I'm going to do this both ways. Q is equal to percent times whole. And both of them I'm going to use 24. And one of them I'm going to use the difference 6. And the other one I'm going to use the difference, or the whole price, which is 30. So if I divide by 24 and I divide by 24, this is going to give me 0.25, which is 25%. And for this one, since this is giving me the quantity of the final amount, this means that what I'm going to get is I'm going to get whatever the answer is plus 1. So it's got that 100% of the original still stacked into it. And so when I do this, I get 1.25, or 125%. And the difference between these two is the fact that this one talks only about the quantity of change, only the quantity or the percent of the markup, and this one talks about the final. So the final is 125% of the original, which means that you added an additional 25% in. So really it's the same problem, the same way to do it, except you're paying attention to things in a slightly different way. So you can recognize that when you do this problem that you can do it either way. You just need to make sure that you identify carefully which method that you are actually using. Let's look at our aim for today. Alright, today's aim, Kipsters will be able to solve for percent error. So percent error is a really important concept, especially when it comes to like engineering and manufacturing. They make machines that create things, but machines even are not perfect. There's going to be some amount of error anytime anybody makes anything because almost nothing is exact. Yeah, maybe it's only like 1/100,000th of an inch off, but there is going to be some amount of error anytime that you're creating something. So right now we're going to look at this and we're going to talk about absolute error in terms of looking at a monitor screen and somebody who has measured the monitor screen. So imagine the situation right now that you pull a new monitor out of a box. The box says that it is 15 inches diagonally. So three different students, Taylor, Connor, and Jordan, go ahead and step up and make a measurement of the box or of the monitor, and each of them measures it twice. As you can see when you look at their measurements, each of them measures it a little bit differently each time. Neither of them gets it exactly the same each time, and a lot of that has to do with how well did they place their ruler, the fact that the ruler doesn't quite make it all the way across. There's kind of like some movement of the ruler, so there's lots of places where there can be a little bit of error created. So as a result, this is what each of them got. Taylor got 15.25, and then the second time got 15.375. So the real question here that we're trying to really think about is, who's right? Who correctly, measured this? Well, the first thing we have to think about is the box says that it's supposed to be 15 inches. Discuss with your partner, are we certain that the box is going to be right? Why would we have any idea, or why would we think that the box is actually wrong? So go ahead and have a quick discussion with your partner. The box says 15 inches. Are we certain that that's right? So the next question is, well, nobody has the right answer, so who here measured it correctly? Did anybody measure it correctly? Turn and talk with your partner about that. And then the final question is like, if none of them measured it correctly, then who is the most right? Looking at this, who would we think is the most right? So when we look at this, I think the conversation about who is the most right can get a little bit complicated when we compare Taylor's measurement of 15.25 to 14.75. We might say that one of them is most right because it's 25.25 off, or that the other one is also 0.25 off. So in this particular case, when we're thinking about who's right, we can't really identify which is more correct, being over or being under. So when we think about this, this is when we use the concept of absolute error. Absolute error is suggesting to us that it doesn't matter how far off they actually are. It just matters that, or it does matter how far off they are. It doesn't matter which direction off they are. So basically we're saying if we take their measurement, and we're going to call their measurement M, and we subtract away what it's actually supposed to be, we're going to get a value. But we actually don't care what value it is, whether they're off in one direction or the other. If you think back to some of the work that we did all the way back in Unit 1 and Unit 2, what did we do when we didn't really care about direction? What operation or what symbols did we use to help describe that? Turn and talk with your partner, see if you can come up with what was that concept that we had when direction didn't matter or when sign did not matter. So the concept you should be thinking of is absolute value. So whenever I'm finding absolute error, I'm going to use absolute value. So when I do M minus A, so I'm going to look at Taylor's measurement 1 as an example. All right, the measurement that Taylor had was 15.25 minus the actual, which is supposed to be 15.00. And that is going to be the absolute value of 0.25. Alright, so this is a positive 0.25. Absolute value says it doesn't really matter. I just wanted to be able to compare it. 0.25. Let's look at Connor's measurement 1. Connor's measurement 1, same idea. Absolute value of the measurement minus the actual. His measurement is 15.5. The actual is 15. So again, this is going back to assuming that the box is right and that the box is that the item is actually 15 inches. We do that subtraction, we're going to get the absolute value of 0.5. So his absolute error, he's off by 0.5. And finally, let's look at Jordan's measurement 2, which is 14.75 minus the actual of 15. Now when we do this one, switch the opposite, we see this is going to be more negative than it is positive. So we get the absolute value of negative 0.25. So again, I don't really care which direction they're off. I'm just trying to figure out absolute error. So exactly how far off are they in general? So it doesn't matter to me whether it's negative or positive. That's why the absolute value tells me, hey, I just want to know they're 0.25 off. This is the concept of absolute error. So this tells me how far off they are in terms of the measurement that's being given. All right, so, but a lot of times we don't really care about the absolute error. When I start to think about some examples here, is like if I have a small, rubber ball, maybe this rubber ball is some part of some larger item. Maybe the rubber ball is supposed to be 1 inch in diameter. Now imagine that's off by a whole inch. Is that going to be making a huge difference in its or whether it's actually going to work into this item? Now, if I take the same thing and I have a giant beach ball that's supposed to go into this particular item and it's off by 1 inch, is that going to make as much of a difference? The answer you should be thinking about is the smaller something is, the bigger difference every inch is going to make. And so when we think about it that way, what we want to think about is that percent error is actually more important than the absolute error. So if I have a giant, 200-inch thing and it's off by an inch, that's really not that big of a deal. But if I have a 1.5-inch thing and it's off by an inch, that's kind of a big deal. It's almost double the size that it's supposed to be, which could be really bad. All right, so finding the percent error means that all we're really doing is we're finding the amount of the error as a percent of, so we're finding the error is a percent of the actual. So our formula here is really area. The percent error is the amount of error, the absolute error, divided by the actual. And this is just a little bit of work to prove what that is. So the absolute value of the measurement minus the actual over the actual. And that comes from back over here when we solved to find the absolute error. So we've already done this work for Taylor's measurement 1 and got 0.25 was the error. Alright, so the absolute error was 0.25. The actual is supposed to be 15. And then when we do this division, this is going to give me my percent of error. And when I do that calculation, I'm going to get 0.016 repeating. So if I want to change this to a percent, move the decimal 1 2 times. This gives me 1.6 repeating percent. So they're 1.6 repeating percent off. Alright, from example 1, part B, find the percent of error for Connor's measurement 1. What does this mean? So go ahead and you're using your work from part B. Go ahead and find Connor's percent error. So Connor's percent error is going to be his measurement minus the actual divided by the actual. We already found his percent error is 0.5 over the actual is supposed to be 15. When we do that division, we're going to get 0.033 repeating. Move the decimal 2 times. This is going to be 3.3% repeating. So what does this mean? Turn and talk with your partner. What does it mean that he's 3.3% off in comparison to maybe Taylor's measurement? So as we look at this, what this tells us that is, for every 3 that out of 100, he's going to be off a little bit. So, and when we compare this to Taylor's measurement, we can see that one of them is 1.6% off, and one of them is 3.3% off. So Taylor is more accurate than Connor because his error is less. His error is less. His mistake is smaller. All right, from example 1, part C, go ahead and find the error for Jordan's measurement 2. What does this mean? All right, so go ahead and find the calculation for Jordan's measurement 2. So again, looking measurement error, the error of his measurement, which we did already, we got was coming from here. We did that calculation, was 0.25 divided by 15. And we've actually already done this calculation. So the difference between Jordan and Taylor, if we look at this, they have different measurements, but their error is the same because they're off but in different directions. And so this tells us that for both of them, we actually get this 0.016 repeating or 1.6 repeating percent, which tells us that their error is equally error, but maybe they're off in different directions. So part of the purpose of finding percent error is to allow us to compare even when errors are in different directions. The other purpose is, again, thinking back to that conversation about, 1 inch difference on a beach ball is not the same as an inch difference on a small, like 1 inch bouncy ball. All right, so let's flip on over and look at a couple more practice problems. All right, this first one asks us to calculate the percent error for problems 1 through 3. I'll go ahead and help you out with the first one, get you started, and then the rest of them you should figure out on your own. All right. So this asks us a realtor expected 18 people to show, and 25 people attended. So which one of these we have to think about is the actual, which actually happened? Well, the 25 people is what actually happened. So when we set our equation up or our expression up, our actual is 25. So our measurement or our guess was 18 people. And our actual was 25. And so our equation should set up like this. So this one's a little bit different because it's not like an actual measurement. Our measurement, sometimes we need to think about as being our estimate or our guess. So a lot of times this will happen when you're making predictions about things and how far off was your prediction. So in this particular case, we'll think about our measurement as being our prediction. So our absolute value, this is going to be the absolute value of -7, which is 7 over 25. When we do this calculation, we're going to get 0.28 or 28%. All right? So that's just the full process. When we see a problem like this, go ahead and look down at the next one. Between you and your partner, first determine what is the actual and what was the measurement or the estimate. All right, so hopefully you and your team have decided that when we look at this one, we were weighing a 300-gram mass, so that's what it actually is. And when Tim weighed the object, his measurement was that it was 328 grams. Now, maybe that's Tim's fault or Tina's fault, or maybe that's the fault of whatever they were using to measure it. But whatever it is, there is an error in that measurement. So we want to find the percent error. Go ahead and use the percent error expression to go ahead and find the percent error for this. Make sure that you've paused the video and you've finished it up first. But when we look at this, our measurement was 328. The actual is 300. Meaning they were off by 28. And the actual was 300. So 28 divided by 300 is going to be 0.093 repeating. Move the decimal 2 times. This is 9.3 repeating percent. So he's off by 9.3%. Finally, look at the last one. Again, identify for yourself in this particular problem which is the measurement and which is the actual. Think about that, and then go ahead and solve and find your percent error for this problem. So as we look through this, what we see here is that recorded that he had bowled 250 points. However, the official scoreboard showed that Darwin actually bowled 225 points. So I think in this one it's a little bit hard to decide, which one is the actual. And so we have to think about the actual is, well, it doesn't really matter what he thought. The official or the referee is going to be the correct one. So I'm going to go ahead and count this one as the actual. If you did it the other way, you're going to get a different answer. And I think with this one, I'm not going to argue with you too much if you decided that 250 was the actual, because this is really boils down to who's right, the official or Darwin. All right, but if I do it my way, my measurement minus my actual, I said my actual was 225. It's going to be 250 minus 225. It's going to be 25 over 225. When I go ahead and do this, this is going to give me 0.111 repeating, which is 11.1%. All right, last problem. It says the attendance at a musical event was counted several times. All counts were between 573. The actual attendance is between these two numbers inclusive. What is the most percent error could be? All right, so we know the numbers between these two things. And so the question is, what's the most we could be off here? What is the highest absolute error we could have? If we know it's between these two things, what's the highest absolute error we can have? Turn and talk with your partner. What is the most you could be off if you know for a fact, at the very least, that it's between these two numbers? So looking at this, we want to think through this, and like the worst case scenario is that I know it's between these two things, and I guess that it's 589, and the actual is 573. This is the worst case scenario. This is going to be the greatest amount of absolute error that I could possibly have. So when I do that, that's going to give me that the worst my absolute error would be 16. Now, maybe we do it the other way around and we get our absolute error is 57 and it's actually 589. So the question is, now, which would be worse if I was off by 16 and my actual was 573, or if I was off by 16 and my actual was 589. Go ahead and put those into your Chromebook calculator and determine which one would actually be worse. So this one is approximately 0.028. Again, that's rounded. Approximately 0.027. So this is 2.7% off, and this is 2.8% off. Now we can see that this one here is the greater error. That is the most percent error. Now, before we move on, I want to ask, is there a way we would have known, even before doing the calculation, that this one was going to be the greater error? Is there a way we would have known that? Turn and talk with your partner. Is there a way that we could have known that that was going to be the greater error? So when we talk with our partners, what we should know here is that when we look at this problem and we go ahead and look at these, they have the same numerator, so it's like 1/2 and 1/3. Which one is going to be greater? Well, if we're dividing by a smaller number, that's going to give me ultimately a larger percentage. So actually, I never even had to write this one down if I didn't want to, because I would have known that if I put the smaller number in as my denominator, even if I didn't know which one it was really going to be, this one was going to give me the greatest error. All right, so that's our work for today. Please go ahead and move on to your alone time. You've got 2 problems. Once you're done with your alone time, please go ahead and be working on Khan Academy.